Okay, so momentum. Think about something that has a lot of momentum. Everybody got something? Oh, by the end of the day, you'll be able to describe and calculate momentum of an object and describe and calculate impulse and how that relates to momentum. So the nice thing about momentum is that the things that you've concluded throughout just you hearing that word actually works out okay. The variable for momentum, we'll do the equation first. The equation is mass times velocity. Hopefully, the thing that you pictured. No, still working. Okay. Hopefully, the thing that you envisioned that has a lot of momentum is really massive and it's moving really fast. Okay. Now, here's the wacky thing about momentum. The variable for momentum is a lowercase p. Like, why? I don't know. We kind of ran out of letters, and momentum got the leftovers. And momentum. Okay. So, if something is really massive and moving really fast, it has a lot of momentum. What would cause momentum to have, sorry, what would cause an object to have no momentum? Assuming that all objects have some sort of mass, you would have to have a velocity of 0. So if it's at rest, it has no momentum. Good with that? Okay. The unit for momentum, what is the unit for mass? Kilograms. And the unit for velocity is meters per second. Now, usually in physics, when you have a conglomerate of variables like that or units like that, they usually come up with a famous scientist and say, yeah, we're just going to give them their last name. Like you've got newtons, you got joules. Again, momentum gets the shaft, and we ran out of scientists evidently. I don't know, but like it's just kilograms times meters per second. Okay, not very convenient, but yeah, that's what we got. Okay, so is momentum a scalar or a vector? Does mass have direction? Does velocity have direction? Okay, so it is a vector and it has the same direction as velocity. Okay, the way it is moving. If you guys want to sit over on that side, you're welcome to. But there's actually perfect number of desks. 1, 2, 3, 4 right there. But whatever, your choice. Okay, so whatever direction it is moving, that's the direction of momentum. Okay. All right. If you're going, if a team, athletic team, was going into a tournament with a lot of momentum, you would not want to be playing against them. Okay. A way to describe momentum is how hard it is to stop something. If you have more momentum, it's harder to stop. And do that. All right. Let's jump to this. Is it possible for a 500 kilogram sports car to have the same amount of momentum as a 10,000 kilogram Mack truck going down the road at 20 miles an hour? Tell your neighbor. And how, if it is, how would you make that happen? Correct answer is yes. Okay. But what would you have to do to the sports car to make that true? Go really fast. Okay. It might burn up in our atmosphere so fast. But anyway, next question. Tell your neighbor. Correct answer is C. Both experience the same acceleration of gravity, 9.8 meters per second squared, over the same distance, going to hit the ground at the same time. That means they're going to have the same speed, but the one that has more mass is going to have a greater amount of momentum. Okay. I'm just going to tell you the answer to this one. Correct answer is no. Because at this moment in time, this one's moving north, this one's moving south. Okay, they have the same magnitude of momentum, but their directions of travel are different at that moment in time. But they're both going around the same racetrack. Yep. But one's going this way, the other one's going that way at that moment. Now, if they're on the same straightaway, then they would have the same momentums. Okay. Here's where I want you to walk away from, or here's what I want you to take away from this. Momentum has direction. Okay. Momentum has direction. Talk to your neighbor. Tell them why you think so. Correct answer is E. Every egg enriches eels. All right. That'd take a long time. All right. So when we were talking about change in momentum, in this class, we're assuming that the mass of the object does not change. Okay. In this class, we're going to assume that as you're walking along, your arm doesn't just fall off like hate when that happens. Okay. We're going to assume that the object stays intact. The mass does not change. So in order to change momentum, it's just reflected in this class about if velocity changes. Does that make sense? So you have mass times final velocity minus initial velocity. If your initial velocity, I'm making these up, is negative 5 meters per second, and then your final velocity is a positive 5 meters per second, the math says this: final positive 5 minus a negative 5 is essentially the same thing as 5 plus 5. You get a change in 10 meters per second times whatever mass you had. Good with that? So watch that momentum has direction. Good. Versus the other, one of those was 0. Okay. Oop, you don't know that yet. All right. So if the net force on an object was equal to 0, some of the forces are equal to 0, what would happen to the object's momentum? If the net force was equal to 0, what would happen to the object's momentum? Talk to your neighbor. Correct answer is it would stay the same, remain constant. Okay? You know that if it's the net force is equal to 0, the acceleration is equal to 0. Therefore, your velocity is not changing. So the momentum remains constant or unchanging. Okay? So if the net force isn't equal to 0, if there's an unbalanced force, what does that mean happens to momentum? It changes. Okay? So then the follow-up question is, well, by how much does momentum change? Okay? So it turns out that if you take the net force, the total force, and you multiply it by the time at which that force acts on it, that is equal to change in momentum. Okay, so we know that an unbalanced force causes a change in momentum, but how much does it change by? Well, we take that force and we multiply it by the time at which it acts on it, that yields that much momentum change. Okay, we have a name for this quantity of force times time. This quantity is known as impulse. Okay, it has a similar flavor to work. Like we came up with this quantity of force multiplied by distance that changes the energy a certain amount. Okay, force multiplied by time rather than distance yields how much momentum changes by. Okay. Good with that. So the longer the force acts on an object, the greater the change in momentum is going to be. Good with that? All right, the unit for impulse. What is the unit for force? Newtons. What is the unit for time? Seconds. And Newton times a second, that is the unit for impulse. Okay. Now, you don't have to reproduce this, but I'm just showing you for peace of mind. What is the unit? What units make up a Newton? Mass times acceleration. Get that? Times seconds. How does this simplify? Kilograms times meter per second. Hey, isn't that the same unit as? Why, yes, it is. And that will always happen. Has to. Okay. All right. Last thing. So some people's understanding of force and momentum kind of get tangled together. They are not the same thing at all. To say something has a lot of force, like, whoa, it has a lot of force, that is not a good physics statement. Okay. But you can say, whoa, that thing has a lot of momentum. Like, that's legit. Okay. Things cannot have or possess force. You're not a Jedi. Sorry. Busty bubble. A force is something that acts on an object from the outside world, from another object, like, oh, okay, experienced a force. Good with that? So just want to get that out of there. All right. So here, this is a good reference tab up top there. Tell your neighbor. Correct answer is B. Let the equations guide your thinking. You experience a same force for a greater period of time. Therefore, your momentum is going to be, the change in momentum is going to be greater. Good with that? Okay. You really didn't have to take physics to be able to answer this question. Correct answer is A. But what I want you to do is take a no-brainer question and use, like, see how the math supports that. Okay. The golf ball had less momentum initially, therefore experiencing a force for less amount of time to get a smaller change in momentum. The bowling ball had a greater change in momentum. It's going to require that same force more time to act on it in order to slow it down. Okay. Follow-up question to that. Tell your neighbor. Correct answer is B. Okay. They have the same change in momentum, same force. You have to have the same amount of time. Okay, these are more like warm-up questions. These next 5 are a little more test worthy. Talk to your neighbor. What do you say? Correct answer is B. Okay? The change in momentum we're saying is identical. So if you have half of the force, in order to cancel this out, to keep this the same, you need to multiply your time by 2. Make sense? Mathematically? Thumbs up when you have a guess. Have a conversation.
Wait, are you starting from rest?
Yes. Correct answer is alphabet soup. All right. When you are doing this and answering the question, what is the change in momentum? There are two different perspectives to look at it. We can look at it from the mass times change in velocity point of view. We can look at it from the force times time point of view. One of which is going to be rock solid. It's going to be definitive. It's like, boom, take that to the bank. That is like definitely the right answer. The other one's going to be like, I'm going to call that fuzzy. Like, okay. Here's the rock solid, definitive, same force for the same amount of time. Therefore, they will have the same change momentum. There is no way around, like, same force, same time. Has to be same change momentum. This way, in this example, is fuzzy. You're like, well, A is more massive. It's probably not going to go as fast. A or B is not as massive. It's probably going to go faster. I don't know. It could be the same. You see the fuzziness? It's not. But this is definitive. Like, boom, same force, same time, same change of momentum. And then you can use this to help identify the fuzziness, like take away, bring some of the fuzziness in focus. Okay? But you're looking for the rock solid, definitive argument. Okay? Sometimes it's going to be the other way. It depends on the scenario. Okay? Correct, oh, sorry. Correct answer was B. Same time, same change of momentum. Okay? Talk to your neighbor. Correct answer is C. No, not C. B. Okay. Experiences the same force for the same amount of time. Therefore, they will both experience the same change in momentum. Okay? Now, A is going to have a greater momentum at the end. It will. It has more momentum. It's going faster. Okay? But it is, it's not asking for the final momentum. It's asking for the change in momentum. If you have an unbalanced force acting on an object, it will experience acceleration. Remember the skateboarding lab. Okay? You will experience acceleration. You will speed up. Now, A is going to go from like, I'm making these up, going from 30 meters a second to 50 meters a second. Where B is going at 10 meters a second and goes up to 30 meters a second. Both experience the same change of 20. That's what this is talking about, not which one has more momentum at the end. Okay? Good with that? Good? Okay. Thumbs up when you have a guess. Talk to your neighbor. Tell them why you think so. What do you say? Got a one vote for B. One vote for A. 2, 3 A's. Okay. Who wins the race? B wins the race. No fair. You had a running head start. Right? B wins the race. In order to win a race, what does that mean about the time it took you to do the race? Takes you less time to do the race. Therefore, A had more time that force was acting on the object. Therefore, it experienced a greater change in momentum. Correct answer is A. Does that make sense? A spent more time on the track and experienced that force for a greater period of time, greater amount of time. Last question of the day. Did I say that out loud? Nothing personal taken. Thumbs up when you have a guess. Have a conversation. Tell them why you think so. Correct answer is A. Which one wins the race? B. Why? Has less mass. Experiences a greater acceleration. It's going to speed up faster, quicker. Okay? Here's a misconception. Ready? Do not quantify, do not determine momentum solely upon velocity. It's mass times velocity. Okay? B is definitely moving faster by the end of the race, but it's mass times velocity. Okay? Correct answer is A. Has more force. Sorry, same amount of force for a greater amount of time. Good with that? That is today. You got a worksheet due on Tuesday.